So now we're going to talk about how do we take when we have two different variables, we want to look to see if there's a relationship between those. And this is what we do a lot in statistics is we actually are trying to see is there a relationship going on between two or more different variables. So we're going to be talking about a method called regression. Regression is where we're finding that relationship between two or more variables. So you're going to have one variable, which is your response variable, and you could have more than one variable that's your explanatory variable. We're going to be looking at linear relationships, but there are other relationships that you can look for. Linear is just one of the many that we have. There are many, many more relationships that exist out there. And then correlation is a word that we hear a lot these days. People like to use that word, but I don't think people really know what correlation means. It's actually just a measure of how strong the relationship is. It's not a way of telling if there is a relationship. It's just a measure of how strong it is. People seem to think, oh, they're correlated, so therefore there's a relationship. So be very careful with correlation. Also, correlation does not necessarily mean that there's a causation relationship. One thing may not cause the other. Sometimes it does, but sometimes it doesn't. We're going to be looking at both of these in this class, but correlation also has a problem because correlation does not work very well if you have more than two explanatory variables. So correlation only works if you have one explanatory variable and one response variable. So the other method we use is a method called the coefficient of determination, which actually looks at how much variability there is in one variable, in the y variable, in the response variable, and how much of that is based on explained by the model. So we'll be looking at that instead. Again, we're going to start with regression. We're going to find linear regression between two variables. So you need to remember that we have two different types of variables in mathematics. One is called the independent variable and one's called the dependent. In statistics, the independent variable is that explanatory variable. You can also sometimes call it the predictor variable. I don't like that word. I prefer the explanatory variable. And that's the one that explains what's happening. And so we usually use X for that in math classes, so we'll probably use X in this class also. But you can also use words and not use X at all. We also have the dependent variable. In statistics, that's the response variable. You can also call it the prediction variable, but I prefer response variable to it. And in math classes, we usually use Y for that. In this class, you can use the words or you can use Y. It's up to you. I will mention that you could have more than one explanatory variable, but you will only have one response variable. So let's take an example. So wearing a mask to protect against COVID-19 is suggested by the CDC, yet there's still opposition to this use of masks. Data was collected for each state to assess what percentage of the state residents wear a mask all or most of the time in public versus the percentage of people in each state that says they know someone who has in the community has had a virus symptoms. This data was collected by Delphi COVIDcast with Carnegie Mellon University. Though the data was actually collected in cooperation with Facebook, it is considered to be a representative sample of response from residents in all states in DC. So normally I say don't use Facebook as an example, but in this case, the statisticians at Carnegie Mellon University felt that it was a good example to use, and they felt it was representative. So here's our data set. We're going to go grab this data set, and we want to find out what does this data tell you about wearing masks and COVID-19 incidents. So I'm going to go ahead and put this into RStudio. So here's my RStudio, and again, I'm going to read this in. So I'm going to put this in to my console. You can actually use an RMD file, and that's fine. I'm just using console here just because of ease for using it, but you can certainly also have an RMD file. I also want to mention that we do need to have the package Mosaic turned on. So you're going to come down till you find Mosaic and make sure you turn Mosaic on. It's here somewhere. And the way you make sure you turn it on is you check the little checkbox right here, check that box, and it will load that library. So we're just kind of loading that library and having it all in there. The COVID data is right here. I can click on it, and here's what it looks like. It has a state, a location, whether it's west, south, northeast, what restrictions that state may have. Some of them have none, some are minor, some have major, some have moderate. Then this per simp is actually the percent of people with symptoms that somebody knows with symptoms. So the percent of people who know somebody with symptoms, let's put it that way. And that's only in their community. I know somebody with symptoms, but they're not living in my community. So this is basically for your community only. And then the per mask is the percent of people who use the mask. Each row is a different state. So in this case, our unit of observation is a state. And then we have these different variables we measured off of them. Some of these variables are qualitative or categorical. State, location, restriction, those are all categorical because they're just names. The per simp and the per mask are quantitative because they're numbers. All right, so we have our data here. And what I'd like to do is I'd like to see what we can do with it. So let's first try to figure out what would be our response variable and what would be our explanatory variable. So our response variable appears to be what's responding to it is the percent of people who know someone with symptoms. So that's my response variable. We use in this class, we're going to use Y for that. Again, you can just use, you don't have to, but it's a little long to write if I don't use Y. So I'm going to use Y just because I don't want to have to write these words every single time. That's the only reason we use letters is because it's too long to write them. Our explanatory variable appears to be the percentage of people who wear a mask in public most or all the time. And by the way, these are both in states. So the percent of people in a state. And this is percent of people in a state. Again, that one's my explanatory variable. I'm going to go ahead and use the letter X for that. It just makes life a little bit easier than having to write the whole words out every single time. So we now have a response variable. We have our explanatory variable. There are other possibilities for the explanatory variable. This is the one I'm looking at right now. You can have other examples. What I like to do is I like to graph it. I like to graph this data. When we do that, we use something called a scatter plot. And a scatter plot is where you graph the graph of the response variable versus the explanatory variable. So I want to go ahead and do that. I'm going to actually go ahead and use RStudio to create this. To do this, you're going to use a GF for graph function. And the scatter plot is called point. Then you always start off with your response variable. So my response variable was the per simp. And then you do tilde your explanatory variable. That's why it's important to kind of label these as response and explanatory so you know what order they go in. And then you can put them in the right order. Then I have data equals COVID. And then it's always nice to have titles. You can have a really long title trying to explain what this is, or you can just say it's COVID-19 data. And that might be a little bit easier to work with. So there's my graph. I'm going to go ahead and I can copy what I typed into R. If you're using an RMD file, you don't need to copy them. But if you're not using an RMD file and you're just using a console, then it helps to copy what you have. Then come over here to my graph. I can export it. So I'm going to copy it to the clipboard. Remember, you do Control C, or not Control C, right click, and then to copy the image. And then we'll go back and put this in my work where I am. All right, so here's my data. And looking at this, I can kind of see that I seem to have a nice kind of relationship going here. And I want to be able to describe what this relationship is. A lot of people like to say, well, as the percent of mask users goes up, the percent symptoms goes down, and that's a good relationship, but there's more to the relationship than just that. I'm going to describe how are they related, not just what is happening, but how are they related. So in math classes, we talk about different relationships. One relationship is kind of the one we're seeing here, is where you have the dots that kind of follow a line. And we call this, when you see that, linear. There are other relationships we can see. Another one we might see is one that might look something that looks more like this. And that one would be more what we call exponential. Another one that you might see, and there's lots of these, but there's another one you might see, is something that kind of goes up and then back down and then back up and then back down. This is what we call periodic. And again, in your math classes, you probably saw ones which talked about the different relationships. You want to kind of think about what graph, which one of these you might have. Again, there's others. There's lots of other ones. I can't draw them all, but there's lots that we have here. And looking at this one, it looks like I can think of these as going kind of linear. So it's not perfect, but it's kind of close to what it is. So this one is linear. Again, it's because I can actually think about drawing a line in here. And so what I want to do is be able to kind of talk about what is that line that kind of maps these. Because what I'd like to be able to do is I'd like to be able to say, here's a value and predict another value from it. So I'd like to be able to give you an X value and predict the Y value. I'd like to give you the percent of people who wear masks and predict the percent that actually know people with symptoms. So I'd like to be able to do that. So I want to be able to come up with this equation. And so, oh, I should also mention that it's not just linear. I forgot to mention, it's also linear negative because it's going as one increases, the other one decreases. So the negative is also important. If you just say negative, then you've left off more information about what kind of relationship. If you just do the linear and leave off the negative, then you kind of left off what kind of relationship it is and how it's changing. So both words are needed to describe relationships. The other thing I did want to mention is that we want to try to figure out what this is. And if you don't know if it's linear, then it's hard to figure out what kind of relationship it is. So you need to have that information to know, oh, I want to look for an exponential. I do a different way of calculating that. So that's the other reason to know if it's linear or not. So we're going to talk about how to find that linear model. Again, linear equations in math classes is y equals mx plus b. And so all we need to do is figure out what m is. M is your slope. And 0b is your y-intercept. But I'm going to instead of using those words, I'm going to use slightly different words in this class. In this class, we want to actually think of slope as being the coefficient of the x variable, of your variable. So think of this instead of as a coefficient of your variable. And then the y-intercept is still a coefficient, but it's the intercept coefficient. So think of that as your intercept. And you're going to see why I want to do that here. The other thing I should mention is that we have several y's. I have y's in my graph. I have these values. Every single one of these values has a y value. Every single dot here has a certain y value. These are the ones we measured. So I have y's as what we measured. This y is going to be calculated. It actually comes up from my line. And If you think about it, I've got a line here and I've got all these dots. I want to kind of have a way to kind of show the difference between the y and the dots. They also came from sample values. This y is going to be calculated from a sample value. And so we actually will call this y hat. So y hat is the y from the equation. It's the equation y from a sample. And this is a sample because they didn't ask everybody in the states. They have all the states, but each value in the state was just an estimate from that state. They didn't ask everybody. Oh, sorry. So what we need to do is we need to go find that equation. So let's go figure out how to get that equation. And it's really difficult to come up with what that is. In your previous math classes, you could find M and B because you only had 2 points you were working with. We have way more than 2 points here. We have a lot more points here. And we need to come up with how to find that. So we're going to use technology for this. You wouldn't want to do this by hand. All right, so the technology we're going to use is we want to come up with a linear model because we did see a linear relationship there. So it's an LM for linear model. And then we're going to put in always your response variable first. So percent symptoms, tilde your percent mask, your explanatory variable. So response variable, tilde your explanatory variable, and then you have to say what the data is coming from. And then you hit enter, and it gives you the information. So I'm going to go ahead and copy this so we can use it. We're going to talk about this on the next, back over here. I'm just going to copy, put this where I am. I'm going to make this a little bit smaller. It's a little big here. All right. Okay, so what we have here is at first, this is the command I typed in, linear model, response, total explanatory, and then the name of the data set. And then it's just telling you it's calling, it's using the linear model and the formula equals, and it just tells you what formula it was using. So you want to make sure it's the same one you wanted and where the data set came from. And then again, these were coefficients. This one's called your intercept, so that is your B. So right here, this one's called intercept, so that's your B. This is the coefficient of your mask. Remember, the mask is the X variable. So if this is the coefficient, that's your slope. So we can now say that we have y hat is equal to 114.825, that's my intercept, minus 1.085x. So there's my equation. So this equation is what we have now. And I can now use that equation to find that information. So if, let's say I have 68%. So let's say 68% of the people in a state wear the masks in public most or all the time. So I already wrote that that was my X, but once you get this equation, this information, you know that that's your X because that's the people in the state wearing masks. That was your X variable. So we know to put that in for X. So we're just going to go ahead and take our equation. Y hat is equal to 114.825 minus 1.085 times X. Now, normally percentages are written as decimals, but let's go back and look at the data really fast. I notice all of these percentages, because these are percent symptoms, these are percent masks, they're not given as decimals, they're given as percents. So we can actually leave it as the 83 or the 87, sorry. So we're going to put in 87. I'm sorry. I don't know why I had that. 68. I don't know why I said 87. 68. So we're going to put a 68 in here and we're going to calculate this. Now you can take out your calculator. The one on your phone will be fine too, but I'm going to actually use R. So I'm going to come over here. I'm going to use the R calculation. And I can just type sin 114.825, that's my x. I'm sorry, that's my slope. That's not my slope. That is my y-intercept. There we go. And then I've got the 1.085, that's my slope, times the 68. And so R actually would do simple calculations like this. So we can just go copy this. And we'll come back over here and we'll post it in here. And so I know that this is equal to 41%. So in a state when only 68% of the people wear their masks, I have a 41% of people know somebody with symptoms in their community. Let's pick another X value. So let's say now instead I'm going to say that 93% of people in a state wear a mask in public most or all the time. So that tells me my X in this case is at 93. So again, we're going to go find that Y value. So that Y value would be Y hat would be equal to 114.825 minus 1.085 times the 93. And again, I'm going to go use R for this. So back over here in R, I can just use the up arrow and then just change the 68 to 93. The up arrow always brings back your previous answer. Okay, so plug this in. And so I know that this is 13.9 or 14%. All right. So now that I've done that, we can do one more. What I'd like to do is I'm going to go back over here just really quickly. I'd like to kind of see what my data ranges between. What are my inputs? So I'm going to do a DF stats. And I'm going to do it for the per mask. I want to know what the range is of my X variables. My data equals COVID. And I just want to do a summary. And I can see that my lowest number is 63. So when I picked 63, that was the lowest value I had. My highest is 97. What if I picked like 50? What if instead of picking one of these values, I went ahead and said that X equal 50? And I'm not going to write it out this time. You got the idea. So now we've got a Y hat is equal to 114.825 minus 1.085 times 50. And again, I'm going to go back over to R and I'm going to calculate that. I just did a command, so I have to do another up arrow to get back to the one I want. And I get 60.577 or 61. All right, so that is pretty high. If I go back, I do want to kind of talk about these, but if I go back really fast to my graph, 60 is not on this. I mean, 50 is not on this graph. 60 is, 63 is because it's at the bottom here. And so it's saying that the point on this line is about that number, but we just got a 60 something. Let's see, what number did we get? Whoops. We got 61. So remember this value was 61%. The other values were 14 and 41. So what might be helpful, by the way, is we can actually graph the regression line on that scatter plot. So I want to go do that really fast. Show you how to do that. I want to first create my scatter plot again. So I've already got that in here. I can just use the up arrow till I get there. If I do, before I hit enter, if I do the percent symbol again, then that means it will keep what I'm done. It's going to keep that value, and I can then put these together. And I'm going to actually do a linear model. So it's a GF linear model. And what that would do is it will plot my regression line on that scatter plot. I don't need to put anything in this because what the piping also does for me is the piping also will take everything I put in the first command and pipe it into the second command. So I can just not type anything in there and just hit enter, and there's my regression line on there. So I can actually go ahead and export this. I'm going to go ahead and grab that command I just did, just so we see the command again. All right, so there was my command, and now I can see my line here. Oops. I can see my graph on there. And so again, if I went to my 93, it does look like it's right around 14, and all the values are right around 14%. So they're all kind of close to that. When I got down here to the 63, the value we got was 40 something, I believe. Let's go back and look. When I had the 63, 68, we were at 41. So looking here, even the 68, we do kind of see values close to 40 something. So it looks like it's working okay. But now we're down here at 50, we're all the way up here at 60 something. And granted that would do that, but there's no data there. You don't know for sure that that's still happening. So we don't know if that's actually what's going on. And so we actually get what we call interpolation and extrapolation. Interpolation is where you're predicting values, the y values from the x values in the range of the original values. Extrapolation is where you're predicting the y values from the x values outside the range of the original values. And so these values here of the 68 and the 93, those were interpolation. The other one was extrapolation. You got to be very careful with extrapolation. You don't know for sure that that relationship's still existing and still continuing. The last thing is that we also can look at the fact that we have on each of these points, and I'm going to get a different color here. I can use blue. Each point from this point here to the line, we're going to get a value on the line. Each of these points on the line are different values. And I can actually measure that distance from there down. I can measure the distance from any other point to it, to that point on the line. This point here is a y value. The point on the line is a y hat value. And that distance is your y minus your y hat. Those are known as what we call the residuals. And the residuals give you an idea of how far off they are. So the farther the value is from it, the bigger the residuals are. The closer, like this point right here has a really small residual because it's right there next to the line. This point has a much bigger residual because we're much farther away. And we can calculate those. And what we want to do is we want to find those to be as small as possible. This line, by the way, is known as the regression line. It also is the line that best fits the dot. So it's sometimes also called the best fitting line. And it also could be because we're going to take these residuals, some are positive and some are negative. The ones below the axis would be negative, the ones above would be positive. We want to get rid of the signs, so we square them to make them all positive. And we want those residual squares to be as small as possible. So sometimes it's called the least squares line. So there are different names for those. And these residuals are what we can actually look at and calculate. All right, so this is the basic idea behind regression.